independent, of course. So most of them have the oldest code because bulk sales rocks. Cisco salespeople, Cisco is a fully sales-driven company. They make money on the provision, so they try to sell a lot of routers at once, which I highly appreciate because they're all going to have the same Ramon version. So return-oriented programming is something that I think pretty much every hacker that had a need for it invented by himself, and then was surprised that everyone else invented it too. So Sebastian Kama talked about this and called it borrowed code technique. There's an excellent talk from Black Hat this year on return-oriented programming, highly appreciated, because that was actually one of the academia talks where they actually did something right. And it has been shown to work very well on Intels, of course, and on Spark. Now the problem is, what you do is you lay out the stack in a way and then jump into individual functions that are already existing in the code. So you're not injecting actual code, you're just changing the stack so it behaves differently. I have fancy graphics in a minute, don't look puzzled. The problem we have here is it has been shown to work really well with an entire glibc and not the diet one. So we end up having a lot of code, and we have architectures that they use, like Intel, that directly return over stack. Now, in this case here, we have about 36,000 instructions because the bootloader isn't that big, and we return over the linked register. Sucks a bit, but worked nevertheless. So here's how it works. Essentially, you look for code segments in the function tails that you're interested in. Let's say you have this is the code that fucked it up, so here's the buffer overflow, I kept it out, and then you have a return, an epilogue that actually fixes the stack, restores the higher registers, and then you need an epilogue that actually saved the linked register on the stack, and here returns it with the pulling it into R0 and then putting it into the linked register. So you can't actually exploit very short functions because they don't save the linked register on the stack first. So you have your buffer that you can overflow, and then you fill it with stuff up to this point where the saved registers are, and then more stuff, and then you return to the function that you discovered before. This is a function in Ramon, and this is what you need. It's an arbitrary memory write. It takes, for those of you that don't speak, I was about to say PowerPoint, PowerPC, it takes the register R30 and moves it to offset AB to the address where R31 is pointing to. So that's an arbitrary memory write. Now, because the registers are restored here with the data that you put on a stack, they're actually used when you jump here. So you can actually put the value and the pointer into your buffer overflow and then jump to this function. I had it even better animated, shit. So this is where it pulls the information. Then we jump to this function, and then we have the memory write, ta-da. And then, of course, you can chain this. So you can do it again. So you feed it more crap and put this into the linked register, put this into the registers that get restored, and then jump back. That is a well-researched technique, but actually works on PowerPC as well quite nicely. Now, we have a second issue. We have too much cache. A rare problem in those times, but here we do. Exception, we have two different caches. The thing is, the data cache and the instruction cache are entirely independent. They don't inform each other when stuff happens. Because the PowerPC designers figured that most code is not going to modify itself all the time. So what happens is, you have your typical capital A's, you get them in here, you have a mem copy, which is hopefully too long. Then it goes back to the data cache, And then because he doesn't know if the data is going to be changed in 5 minutes or so, he's keeping them in the cache first, which is the purpose of the cache. So it looks like you wrote it to memory, but you didn't. So if you jump to it, it goes boom. And not boom in a positive way. Because it's jumping to the stuff that was there before. So you can't just like write stuff and then jump to it, which sucks. But there is more code in Ramon that we can actually use. Right in the beginning of booting, it actually doesn't want this cache either because it's unpacking the image. So there's an entire function that goes ahead and essentially says, are interrupts disabled? Let's see, disable interrupts, flush all the caches, turn them off, and turn interrupts back on so we have internet. It's cool, so we can jump there and disable the caches. So this is how reliable code execution on Cisco works. You have a stack and an overflow on the stack, right? Now, I'll probably win a prize here for the animation, I hope. It looks like a mess when you design it. So first of all, you return to the function that disables the caches. And you also return to it in the return-oriented programming way. So you're not jumping into the entry point, but you're jumping after it saved the registers on the stack so that you keep stack control. Then you have the return-oriented memory write. So you're writing a move to counter register SP into another memory area I discovered, which is the global data elements that are placed right in front of the image, so they're not image dependent, they're always at the same place, and it's executable and writable in memory. So we are writing this instruction there. Then, of course, we are writing another instruction, which says branch to counter that we just loaded with the stack pointer. And then we jump to this code, which then jumps to the stack, which we didn't need to know where it is because it's taken from the register, right? And then we search the entire memory for a tag. Now, what do you do if, like, Germany has this new trend of losing data? And, well, essentially what we have right now is we lost our data because we need the remaining packet to have the big shellcode, right? So we do what most hackers do. We go to check Fefe block, and then if we find Fefe block in I/O memory, this is where our data is. So we copy this data from the I/O memory, because it's not executable, onto our stack, but on a higher range that is not used. And then we execute our third stage code. I so wanted to show that picture. So, notes on the reliability here. This method is actually reliable for a known bootstrap version. So, I did successfully test it and implement it for the IP options vulnerability, which is a very nice vulnerability, and I hope to show you in a minute. So it's a single packet buffer overflow in iOS. And I also successfully ported it to the FTP vulnerability that Andy Davis exploited, so that my version of his exploit actually is image independent. The second stage code, the one that looks for the block, is actually the less reliable, because here again we have this complexity issue with iOS that they actually place the code, place the memory anywhere they want. So I/O memory is sometimes at a different base address, even for the same ROM. But that's actually, yeah, you can overcome this quite easily by adding more second stage code, but you usually want to keep it small because you want to get away with it. After you got code execution, you actually want to keep the box running, because if you have code execution, then the box reboots, you've won nothing. So, the people that have published exploits so far use terminate process, which is an image-dependent call, of course, because you don't know where the where the function lies. So this is exactly what we don't want. And, well, the vulnerability I was exploiting is IP options, which happens in a process called IP input. Now, this process is kind of crucial because otherwise you have a pure IP output device, and that sucks. So actually terminating this process wasn't an option. But coming back to how our exploit looks like, we have the stack layout. And here's the reason why we try to be really small with the second stage code. Because we can search the stack frame upwards and see if we find a sequence of saved stack pointer and link register that we didn't fuck up already. And then we return to that one. And this is reliable because the depth of the stack and the layout of the stack, especially in terms of what functions return information to functions is on a stack, is a call dependency. Like this exact call path will always produce the same stack trace in terms of what functions are on there. So they will actually need to change the code logic of that exact code path. So this would become unreliable. And it also includes some voodoo that tries to make it more reliable. Shall I demo this? Yeah? This is the point where everything goes wrong, right? We want to see the packets. So it defaults to the most useful packet. What do we have here? Okay, that's good. Now, how was I thinking this works? Oh yeah, one word to the demo. Blah, 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 Shut up. Yeah, it's talking too much. Better. So the thing is this, when we had all the discussions with the government people on the hacker paragraphs, we had pretty much no agreement with them except for one thing, that Hello World programs are not hacker tools. So, since I cannot actually demo this with a shellcode, which is illegal, we have a remote string display program for Cisco iOS. So this is the box. This is the Cisco. Yeah, I'm using the mouse for pointing. And this is my Linux in a virtual machine. And we're just like firing the exploit display program. And we get a statement down there. So what's really cool about this is it's one ping. And it's actually even a valid ping. So the vulnerability lies in the fact that they fucked up to parse the IP options correctly. So what we have here is down there. We have the option EOL, which is end of options, which is a 0. But then following this, there is a source routing option, and the length of the source routing option is actually used because they try to be clever when they answer the ping. They look at the ping and go like, oh, it's source routed. And it's a network test tool. So we should actually answer the same way back. So they're trying to turn around the source route. And the RFC says that the source route can only have 8 hops in it. So they have a buffer, and, well, they were generous. It fits 10. But the length field obviously allows for more. So this is the buffer overflow, and then like the remaining stuff goes onto the stack, and the data here is then all the voodoo I just told you. Essentially, it doesn't just work on PowerPoint. So, let's keep going. So